Okay, so in today's lecture, we're going to be covering Study Unit 7, and the topic is design and implementation. So these are the following outcomes under Unit 7. The first one is you have a thorough understanding of the object-oriented design process and activities involved. The second one is apply and evaluate different models that may be used to document object-oriented design. Evaluate types of design patterns as an area of study, understand key issues that needs to be implemented during software reuse and open source development. Okay, so I know that we had already covered design extensively in Unit 5, and also we covered architectural design in the previous study unit, but in Unit 7 it also comes up because certain concepts of it, obviously, design we know precedes implementation. So certain concepts of it still appear in this study unit. Okay, so we want to have to discuss it nonetheless. So design and implementation. It says it's a stage in the software engineering process at which an executable software system is developed. So here we take the designs and we convert them into an executable software. So software design, as we discussed in the earlier chapters, is a creative activity in which you identify software components and their relationships based on a customer's requirements. So we take what we did in requirements engineering and we get creative and we create visual charts that show how these different objects interact with each other and what kind of relationship they have with each other. Okay, so software design is creative activity which identify these software components and their relationships. And then when you're talking about implementation, it's the actual process of executing or carrying out this particular software that was conceptualized during the design phase. It's the process of realizing the design as a program, converting design into an actual working program. And so we have what we call, obviously, our object-oriented design using UML, and we covered most of the UML models in chapter 5. But the thing that you need to understand is that object-oriented design supports object-oriented programming. Because when you're doing object-oriented programming, the properties of these objects have already been defined for you. You just sort of customize them to your expectations, and you also specify the functions that they carry out. So you need to identify these objects during object-oriented design, where you do models for them, UML models, and then you convert those into a system working version during object-oriented programming. So structured object-oriented design process involves developing a number of different systems models, and these models can be categorized further into structural, interactive, and system context, and so forth. Requires a lot of effort for development and maintenance of these models. For small systems, this may not be cost effective. For large systems, by different groups, design models are an important communication mechanism. So for our very small projects, it may be too expensive or too much of an expensive task, because we're working on a limited budget anyway, to do too many modules. Maybe you may do a couple of models here to understand what kind of features may be there as part of the system. But models are very necessary when you're dealing with large systems, because as you can see, they become an important communication mechanism. How so? Remember that you first start with your requirements engineering, then you develop the design models. And the project team may understand the technicalities behind the requirements engineering process. They may understand all of these system requirements when they're written in a technical manner, but the people that are not technical may need some sort of model. Okay, you show them a use case diagram, and by looking at the use case diagram, they have some sort of picture as to how the system may look. So it's very important as a communication mechanism because you're able to cater for people that are technical and people that are not technical. So object class identification, okay? So this is the process in which you actually look at a particular case study and you try to identify the objects. And there's several techniques that people use to do this. There's several techniques to identify objects operating in a system. We tend to use natural language description of the system. Must be used that is objects and attributes are nouns, operations, and services or verbs. Okay, so we use nouns. We look at the case study. We look at the case study for nouns, and we use natural language description to identify particular or potential use cases and actors. Remember, I told you guys once that don't use too much of technical terms in your object class descriptions. And tangible entities must be used in the application domain. Scenario-based analysis must be used to identify several scenarios which will be analyzed in turn. Okay, so there's two approaches you can take here to identify your object classes. You can look at all the different classifications of nouns. You can look at all the tangible things in the case study. Remember, we do a scenario-based analysis. In the next slide, I'll show you what that means. So we do a scenario-based analysis and we look for things such anything. We call it a thing because it could be a tangible thing, it could be a non-tangible thing, it could be roles played by individuals in the organization, it could be sensor or devices, we're storing information about devices, could be reports on incidents that occur, or data about locations or sites. Okay, so if you look at the case study that follows, we have a scenario of a weather station, and it says that a weather station is a package of software-controlled instruments which collects data, performs some data processing, and transmits this data for further processing. The instruments include air and ground thermometers, anemometers, a wind vane, a barometer, and a rain gauge. Data is collected periodically. When a command is issued to transmit the weather data, the weather station processes and summarizes the collected data. The summarized data is transmitted to the mapping computer when a request is received. Okay, so from here, first thing we got to do, the first step is to identify the tangible things. Okay, tangible things meaning the hardware in the case study. That's the first place you start. What are all the tangible things? Here they talk about instruments, air and ground thermometers. So there's going to be some sort of thermometers, anemometers, barometer, rain gauge, and so forth. Those are the hardwares that we can store data about, okay? And if you look at this next slide, it says that object class identification in the weather station system may be based on tangible hardware and data in the system. So we have a ground thermometer, and an anemometer, and a barometer, and so forth. I know it sounds confusing, but I don't know what these things do. But the important thing to note here is that we look at a case study and we identify the hardware. And that's the first place we start. And then we go to the other ones. What are the non-tangible things that we may need to store data about? The weather station as well, the basic interface of the weather station to its environment, if therefore reflects the interactions identified in the use case model. The weather data encapsulates the summarized data from all the instruments. So there's going to be a particular entity or object that's storing the weather station information about the weather station itself, which particular weather station is reporting this information. Then it's going to be a particular entity as based on a scenario, which aggregates all this data that's coming from the different instruments. Okay, so the weather data itself has a separate entity, then the weather station has its entity, then we have entities or objects for the different hardwares that we identify in the scenario. Okay, and obviously our object classes would look something like this. We have the weather station one, we have the weather data object, we have the ground thermometer object, we have the anemometer object, and then we have the barometer objects as well. And pay attention to this. The object class diagrams or models are different to the regular ERD that we know of. They're similar in the sense that you can still combine and show relationships and so forth. But if you pay careful attention, you'll see that here we have the name of the object, we have the identifier, okay? Let me just do this. So we have the name of the object, which is here as weather station. Then we have an attribute, which could be the ID of the particular, they only included one, which is the ID of that particular weather station. And then we have all the commands, okay? All the functions that are triggered by that particular object. And then by looking at this, all of these object classes, we can take them, okay, during implementation, then we convert these functions into programming functions using any object-oriented programming language such as C# and VB and Java. So by looking at objects, you're able to analyze, okay, these are the objects that exist in my particular scenario, so I need to accommodate for them when I'm doing implementation and programming. And our design models, we talked about architectural patterns and architectural models in the previous study units. So when we talk about design patterns or design models, it's design models show the objects and object classes and relationships between these entities. We have two types. We have static models, and then we have dynamic models. Static models are those that show the structure of a system in terms of its object classes and relationships. So if you picture the diagram I just showed you in the previous slide, it's an example of a static model. Your context diagram is an example of a static model. However, if we say dynamic modules, okay, dynamic modules describe the dynamic interactions between objects. So your use case diagrams, your state machine diagrams, all of those are dynamic modules because they show interaction, the messages being sent between an actor and the system, okay? So we can further categorize our design models into static and dynamic. So again, talking about system context and interaction. System context is designed to have an understanding or overview of the whole system or the architecture of the system. Boundaries of a system are defined so as to determine what features are associated with other systems. So in the system context modules, we're trying to see what are the boundaries of the system and what other subsystems are involved in this particular scenario. And an interaction model is designed to have an understanding of how certain classes are related. I just want to show you an example for those of you who have forgotten. The use case diagram is one such example, and this is the use case diagram for that scenario that we just covered about the weather station. So we have the weather station information system, and then we have the control system. And these are the use cases that are triggered by the weather information system. It reports weather and reports the status of the system itself. And then we have the control system, which is in charge of the instruments, all of these sensors or the hardware objects in the case study. So it can restart them, shut them down, reconfigure them, put them on power save mode, and it grants remote access to the particular actor. Okay, so these are our actors in that particular case study. Also, if you look at the use case diagram, it has multiple use cases, and we can take all of these use cases and we can put them in a table. This table that you see here, we refer to it as a use case description. Okay, a use case description is basically a table that provides additional information about a particular use case. So here they made example with the first use case, which is report weather. So the use case, the name of the use case is report weather. And who are the actors? Okay, we have the weather information system and the weather station. Okay, and then you provide a description of what's actually happening in that particular use case. And then what triggers that particular use case? You describe it in text, what triggers the use case? What is the response after the use case is triggered? So what happens after, okay? And any other additional comments. So the important thing to take out of this is that for each use case in a particular use case diagram, you can use a table, and we call the table a use case description to provide further information about that particular use case. So other examples of design models that we covered were obviously the system sequence diagrams, which show the sequence of object interactions. Then the state machine model that shows how individual objects change their state in response to events. And then other ones, we also spoke about use case aggregation models and the generalization and specialization relationship model. So now we're going to talk about the second part of the lecture, which is the implementation, some of the issues that you're going to face during implementation. So focus here is not on programming, although this is obviously important, but on the other implementation issues that are often not covered in programming texts. Okay, so some of the issues that you're gonna encounter during implementation are not usually. It's very tempting to think that it's only going to be programming issues that are aligned to the code while you're doing the coding, but there are other issues as well. One of them we're going to cover is reuse. The second one is configuration management. And the third one is host target development. So reuse, most modern software is constructed by reusing existing components or systems. So we do not, in this day and age, it's very rare that you're going to find a programmer that's building the entire system from ground up. Usually certain components can be reused because they're already existing in the market. So we're going to cover issues associated with reuse, and in configuration management. During the development process, you have to keep track of different or many different versions of each software component. So how do you, during implementation, because there's different developers that are working on a system, how do you keep track of changes? Okay, those are some of the issues you're going to face. And also we're going to discuss host target development. Production software does not usually execute on the same computer as the software development environment. Okay, so your production environment and your local environment are not the same, and that's going to be a challenge for you as well. And we're going to talk about that in the later slides. Okay, so let's start talking about reuse. From the 1960s to the 1990s, most of new software was developed from scratch. So which means the developers wrote the first line of code to the last line of code themselves. By writing all the code in high-level programming languages, the only significant reuse of software was the reuse of functions and objects in the programming language libraries, okay? Cost and schedule pressure mean that this approach became increasingly unviable, especially for commercial and internet-based systems. So you can imagine in the 90s, it may have been convenient to do so because obviously you didn't have a choice. But now there are libraries that have been written by different people that exist on the internet. So why take the long route? Why choose to write the first line of code to the last line of code yourself, where you can do software reuse of components? And you can imagine that modern systems are so complex. They include all of these complex features. It will take you a long time to write all the code yourself. Certain components can be reused. An approach to development based around the reuse of existing software emerged and is now generally used for business and scientific software. I just want to move to the next slide, and there's 4 approaches that we can use for system reuse. Okay, so the first one is we can do system reuse or software reuse at an abstract level. At this level, you don't reuse software directly, but you use the knowledge of successful abstractions in the design of your software. So one such example, just making reference to study unit 6, you can reuse the architectural pattern of a particular software. That's referred to as reuse at the abstract level because you're not reusing the actual code or the software directly, but we're only reusing the knowledge about the particular software. So reusing architectural patterns could be an example of reuse at abstract level. Then we have reuse at the object level, which is the smallest unit, okay? The smallest unit of software reuse. At this level, you directly reuse objects from a library rather than writing the code yourself. So if there's already a function on a particular software, maybe it's a function on a button click object, okay? We have a button click object and an event that's already been coded by someone else, and we want our button to do the exact same thing. So we can reuse a particular function alone. And that's an example of reuse at the object level, okay? Because we're not reusing a whole component of the software, but we're reusing the particular function that's associated with the click event of a button. And then there's reuse at the component level. Components are collections of objects, okay? So an object is the smallest unit. So then a component, based on what we know about object-oriented programming, I would say a component is like a form. It's like a form and it holds other objects, a collection of objects. So we can reuse forms, okay? We can reuse forms. Components are collections of objects and object classes that you reuse in application systems. And then obviously the highest level of reuse would be reusing an entire system, okay? And this is the system level reuse. At this level, you reuse an entire application system. So these are the different levels, or these are the different options that you do have available to you. Or if you're building from scratch, obviously you need to do some sort of reuse to make your life easier, but you also have the option of buying a solution off the shelf, okay? We have commercially off-the-shelf solutions. In some instances, you don't really need to build the system because a solution already exists on the shelf. You just buy a generic system and apply it to your organization, and you tweak it to whatever possibilities they offer you to tailor it to. So you can see that commercially off-the-shelf systems that can be adapted and tailored to the user requirements. For example, if you want to implement a medical record system, you can buy a package that is already used in hospitals. So if you are a hospital, there's probably other hospitals out there that already implement a similar system that you require. So you can sort of reuse that particular, or buy, you can either reuse some of their components or buy the entire package that already exists. When you develop an application in this way, the design process becomes concerned with how to use the configuration features of that system to deliver the system requirements, okay? So we only focus on the requirements. How can we change or make changes to the features to suit our particular scenario as an organization? So moving on to the next concept, which is configuration management. Managing change. So you're working on a project with other developers, and obviously you're building this system and components, and there's different teams working on different components. So then how do we keep track of the recent changes, okay? So the main aim is to support the system integration process so that developers can access the project code and document in a controlled way, and out changes made, compile and link components to create a system. The following are 4 activities involved, okay? So the activities that form part of configuration management or change management is version management, system integration, problem checking, and release management. So when you talk about version management, when you're developing a system, the very first build that you create would be the first version of the system, okay? So then maybe you create a prototype from that build, you give it to the customer, and the customer has what particular feedback that you need to now go back and make changes, which now you're going to have the second version of the system, okay? So configuration management deals with how do you keep track of the different versions that we've created. This is a process of keeping track of different versions of a system, stops one developer from overwriting code that has been submitted by another developer, okay? People can overwrite your components. If you're working on let's say you're working on the same project and you're working on a folder, then somebody copies and pastes the component that or the changes they've made into an existing folder, and then it overwrites what you did. then you find that they're actually overwriting the more recent version of the component. So there are systems out there that are built to manage version tracking or track versions of different components. And we know repositories such as Git, if you've seen or run across Git on the internet, that's exactly what it's for. It's a repository for tracking different versions that manages this whole process and prevents developers from overwriting each other's code. So system integration, different versions of components which are added or modified to an existing component are compiled and linked to the required component automatically. So there's some sort of synchronization. The computer that you're working on and the repository itself, every single time a particular component is modified, the local component version is synchronized to what's in the repository, okay? And then we have problem tracking as well. Allows users to report bugs and errors to developers so that developers can see who is working on these problems and when they are fixed. So we're able to track problems because all our components are in one centralized repository, and we're able to figure out, okay, so and so is still working on this particular component, or they've already synchronized the recent updates. So the difference between version management and release management is that version management, we're dealing with localized builds, okay? Builds that are on our computers as developers, and we created different versions based on customer expectations or requirements changes. But release management, we're managing releases that have been given to our customers. So now this system has been put to the production environment already, okay? So when you take a version and you release it to your customers to use, we then refer to it as a release. So configuration management, one of the activities is release management, a process of releasing new versions of software systems to our customers. The other implementation issue that you're going to face is that the host environment, which is the environment at which we code and build software, is not the same. The conditions are not the same as the production environment or the target environment. So there is a need to, firstly, you cannot build the software on the target environment, because then everybody, you find that it's a live server that's hosted on the internet and people can see what you're working on before you even launch it. So it's good to separate the two environments, but at the same time, developers need to understand that the host environment, you have all the permissions on your local computer. You test locally, everything works perfect. Then you deploy it to the target environment for production and execution purposes. Then you find that certain components or libraries or databases or related systems are now not compatible. So you need to pick out these compatibility issues. And the way you can work around this issue is do testing on both sides. Don't just say, okay, we did testing on the host environment, so everything is perfect. So then you just send out everything as a release to the target environment. No, also give the system time in the target environment, do your testing properly, see if everything is the components, the architecture is working perfectly, the components are sending each other, are communicating in the format that they should, because you're going to run into some of these problems. And then lastly, the tools that support the software implementation or software development. So obviously during software development, we're going to be using some sort of integrated environment. So your integrated compiler and syntax directed editing system that allows you to create, edit, and compile code such as Visual Studio, a language debugging system. Usually, obviously, Visual Studio is integrated, so it will also have language debugging integrated into it. Graphical editing tools. Maybe you may be using Photoshop to create markups and so forth. Testing tools such as JUnit that can automatically run a set of tests on a new version of a program. There are other testing tools available online at which you can write code and test it online without affecting or without having to edit or test on the actual project that you are working on. And then you also have tools to support refactoring and program visualization. And then we have our configuration management tools to manage source code versions and to integrate and build systems. So to conclude Unit 7, We covered the details that are concerning design and implementation of a system. We covered object-oriented design. We discussed it in detail, including designing of context models and interaction diagrams. And after a system has been properly designed, implementation follows it. Implementation is creating an existing executable of a system. And then the last point we covered is there's a need for proper configuration so as to manage the changing or evolving software. Okay, so there was 2 parts to this lecture. The first part of it, we made reference to design, which we covered already extensively in chapter 6 and in chapter 5. And then the second part of it was what kind of problems are you going to experience during implementation? And the problems that or the issues that we spoke about are not aligned to the actual programming of the code or the errors you're going to be getting while coding. Those will always be there. We talked about the issues that are often overlooked, okay? Such as reuse, your approach to reuse. Are you going to reuse at the abstract level, object level, components level, system level? Are you going to build or buy the solution? How are you going to manage version tracking? Okay, how do you manage host and target development? So these are some of the issues that you're going to face during systems implementation. Okay, so I'll give you guys a chance to ask questions regarding this study unit.